Welcome to the lecture series in computer science. As a part of this series, this is a course on artificial intelligence and we are in unit 3 now. In the last session, I said about the overview of the proposition logic. We started off with the syntactic portion. Today, we will see the semantics, which is in the form of truth table. Again, this is very similar to that of discrete math what you have learned, or Boolean algebra. The same thing we are going to do in the first part of it, followed by the natural deduction rules, which we are going to use for proof. And the first part of it is going to be the forward checking, or the forward means to evaluate the proof. Now, the evaluation of the proposition statements. Remember, we talked about the proposition facts. So, anything that is a fact can be evaluated in terms of true or false. This actually forms the semantics of the proposition logic. So, the steps are: find the value of the basic proposition. Suppose the proposition is in the form of P, Q and R. So, you find what is the meaning behind it in terms of the proposition, and that can be evaluated to true or false. Say we will start with, this is a truth table of negation, and you have two symbols phi and not phi. When phi is true, not phi is false, and when phi is false, not phi is true. This is a simple truth table negation. Now, if there is a conjunction between two proposition symbol phi and psi, suppose phi you think that it is sunny, and psi the temperature is 30 degrees centigrade, then phi and psi it can be evaluated. If both are true, the conjunction is going to be true. If phi is true and psi is false, the conjunction is going to be false. And when one phi is false and psi is true, phi and psi it is going to be false, and when both are going to be false, phi and psi are false. For disjunction, if phi is true and psi is true, this is OR, the disjunction is true. In this case, if you see, when only when both propositions are false, phi or psi is going to be false. In implication, the first case, when both are true, both propositions are true, the implication is going to be true. When phi is true and psi is false, we call the first one as antecedent and this part, the psi, is consequent. So, if there is something, then that is the part behind it. Let us see. So, this part, this phi or psi, this is the consequent. Now, when false and true, it is going to be true. For equivalence, suppose see the arrow, if this equivalent phi is equivalent to psi, if this represent if and only if conditions. So, it would be both propositions are true, then phi double implies psi, or its equivalent psi is going to be true. When both are false, it is going to be true. In other two cases, it is going to be false. Now, this is about the semantics of the proposition logic. Now, what do we call as evaluation? Suppose, how do we evaluate the formula as such? Earlier we saw only the symbols P and Q, and how do we evaluate the entire thing? Suppose valuation is P is false and Q is true, then not P and Q we call it as true. That can be represented as V, this we call it as entails. We call this symbol as entail. And this is a question for you to check whether P and P implies Q, that implies Q as well. So, what you have to do is take P and take Q, find out P and Q, you find out this, then find out P and P implies Q, then the whole thing, suppose I call this as A, the whole thing A implies Q. So, you find the row where this is the entire thing is going to be true, then you can say that whether it is entails or not. We will discuss the answer for this as well as these two in the next class. For this as well as this question as well as this. So, you have to find whether V is entailing not of P and V entails this formula. We have the formula as P and P implies Q, the whole implies Q, and we get the result of this formula as 1, entire thing is 1, which means in all the cases, whether you take this row or this row or the third row or the fourth row, we are getting as 1. In this case, we call this as tautology. Suppose not P, if you get the formula, it is when P is 1, when this is 0, the not P is 1. The other way around, when we take a negation of it, it becomes 1 and 0, which is same as P. This double negation of P. You see, P and double negation of P has the same value. So, we say that if what is contradictory, which says a formula which is never true is called as contradictory. Okay. When P and not P, when P is there, not P cannot be true, and not P is there, P is again according to this. So, both are contradictory to each other. It is always false is contradictory. Satisfiable formula that can be true in some sense. Say if you take this formula not P or Q. Suppose you take not P or Q when Q is 1 and P is 0. So, this would be 0 not of 0 or 1. Not of 0 is actually it is not of false, it is true or true, which is going to be true. Therefore, this formula that is evaluated to be true in some sense is satisfiable. Tautology is something when at all times the formula gets evaluated to 1, like we saw in the previous slide, when for this formula at all possible cases it was evaluating to true, therefore, it is called tautology. So, these are the terminologies we write. So, in this case we write as entails phi, if it is tautology it entails. And what is inference? When we say inference, inference is reasoning. This is the most important part of this logic, and this is taken from the book Logic in Action, which is freely available in the internet, and I will give you also the reference at the end of the session. The inference is written as phi 1 to phi n, where phi 1 is some kind of a phi 1, phi 2 or phi n. These are going to be the proposition formula. And psi also is a proposition formula. So, given these phi 1 to phi n, our job is to find psi. And how do we find psi? By means of some kind of a rules. So, we call something as an inference is valid if at all times when phi 1 to phi n are true, psi is also true, then we call it as a valid inference. So, this has to be true, and this also, if it is true, then we call it as a valid inference, and psi otherwise is called as a logical consequence of this part phi 1 to phi n, and we write the upper part of this phi 1 to phi n entails psi. Now, there are some definition before we get into the reasoning stuff. So, if we say there are two formulas where phi is a proposition formula and psi is also a proposition logic formula, and the same thing will go also for predicate logic. If psi is a proposition and phi is a proposition, then we say if see this here, if phi entails psi and psi entails phi, then we can write both are logically equivalent. Okay. And what is a model? This in logic or in the proposition logic, it is an interpretation in which it evaluates to the true sense. Say for example, we have this formula A implies B. This is true when A is equal to true and B is equal to true. Therefore, we say that the model in A and B where it is true and true, A implies B is true, this is a model. So, this is for the question for you. What are the models in the sentence today is Friday implies AI class. For this case we can have variables like today and whether it is Friday and whether AI class. Another one with today is Friday is AI class, and you compute the formula and see wherever it is true, and that we can call it as a model. And when can we say something is satisfiable? When it has some model, then it is satisfiable. And for example, P and Q is satisfiable when P is true and Q is true, but P and not P is unsatisfiable. Why? At whatever the values P is going to take, or not P will be the opposite of it. So, in that case at all times this is going to be false. Therefore, this formula is unsatisfiable. Say for example, P and Q is satisfiable when P is equal to true and Q is equal to true. Okay. So, for this question again we will do will try it out, and we will discuss more about this in the next class for this question. Now, coming to the other properties of the proposition logic. Okay, this also it is taken from Huth and Ryan, the logic book. Again, the references from whatever I have taken, I will give it towards the end of the class. You can say two sentences, and here the two sentences are going to be the say the from the proposition logic side. So, we say it is logically equivalent. The first one is commutative, where A and B or alpha and beta is beta and alpha. These two are commutative, first two are commutative. The second one is associative. The third is the double negation. This is contraposition, right? Alpha implies beta, logically equivalent to not beta implies not alpha, and this formula is very important because we will be using it regularly, which is alpha implies beta, that is not alpha or beta. This we will be using it regularly, and this also we will be using, and which is biconditional elimination. How do we eliminate this biconditional? The equivalence, put it in terms of and implied condition, and not of alpha and beta is De Morgan's. Alpha and beta we can convert into not alpha or not beta using De Morgan's. It is very similar to your Boolean algebra, and we will also use these two. So, last 1, 2, 3, 4, 5, 6 formulas we will be using it again and again in our AI. Now, there is another term called the knowledge base, like you have heard about the database. Now, what is this knowledge base? Knowledge base, very at the background it is very similar to database. In database what you do is you have a set of tables and you put a query and it will give the response. Similarly, here knowledge base also we will have a set of sentences, and using some kind of a query we will give the query, but we will also get the result. Now, the result is going to be in the form of yes or no, and along with the result we will also get the reasons for why it is yes or why it is no. So, that is the difference between knowledge base and the database. A knowledge base is a reasoning type of method, whereas the database it will just give the answer to that particular query. The reasoning portion is missing in the database, whereas in the knowledge base and with other reasoning techniques it is present. Now, a knowledge base is a set of sentences, like for example, I have given two statements here. Say example, Chennai is hot. This is equivalent to whether when month is May or month is April, and the second statement is Chennai is not hot. So, the two statements here I can combine as Chennai is hot, that implies month is May or month is April, and Chennai is hot. See how I have combined these two statements using this and is combined. These two statements I have combined with and. Now, given these, so far what we have seen is some kind of a definition. We again in proposition logic we started with the syntax. Syntax includes the language of proposition, where with the language of proposition we had some operators in terms of negation operator and the other type of operators and or implies a biconditional operator. And from there we went into the truth tables, and in the after truth tables we also saw that some of the definitions, like what is satisfiability, what is tautology, what is contradictory, and what do we mean by entailment. We saw all that. Now, using that, how do we reason out, how do we put the knowledge base and ask a machine to give an answer and also give a proof according to that. Okay. For that, we will use some kind of a natural deduction rules. Now, there are some natural deduction rules that are available. I will just write it here. So, the first one, we are going to do the natural deduction here. It is going to be, say, suppose I have a statement A and B. I can infer A. This is called conjunction elimination. The second one, this is the labeling of it is conjunction elimination. I have two proposition facts A and B, and I get the inference as B. It is conjunctional. I will put the first one as conjunction elimination 1, the second one is conjunction elimination 2. The third one is I have two facts A and B. I can infer both A and B. This is separate, like last slide we had, today is sunny and today temperature is 30 degrees centigrade. I can infer today is sunny and today is 30 degrees centigrade. And suppose the proposition statement is and, I can infer one of it, that is the meaning behind this deduction rule. We call it as conjunction introduction, and we have either one as A or B and not A, I will get therefore not B. So, this we would be regularly using, and this we call it as disjunction elimination. This is conjunction introduction. This one is this is conjunction introduction, this is conjunction elimination. E stands for elimination, and this is disjunction elimination. Yeah. Another one rule which we would be using mostly is the modus ponens, where you have two rules A and A implies B. Therefore, I can infer B. This is called as modus ponens or MP. And other rule is A implies B and not B, then I can infer not A. This is A actually. This is called as modus tollens. So, these are the natural deduction rules we will be using mostly, and apart from this, the distributive law, the commutative law, De Morgan's law also we will use. And why do we do this? We will use these rules in order to get the reasoning process. So, this is one method of the proof. The other method is using model checking. For our course and our problem as per the syllabus given, we will be using only the natural deduction rules for forward checking. So, let us take one example here. So, we have the first one as phi is equal to P implies Q, L and M implies Q, B and L implies M, A and P implies L, and A and B implies L, A, B. Can we prove the knowledge base entails M? Again, how do we do that? We call something as a premise, if premise is something which is already present in the knowledge base. One, A is available as a premise, this is A, this A is available as a premise, and B is also available as a premise, which is given here. B is premise, and with A and B using conjunction introduction, which I gave earlier. If you remember the natural deduction rules, this conjunction rule A and B, if both are given, then I can conclude A and B using conjunction introduction, and otherwise called as CI. Here I have given as wedge symbol I. Here we are going to call that as CI. CI and wedge I are both are one and the same. So, it is using these two, use A and B using CI, I get third clause. And I already have A and B, this is already available as a premise. A and B implies L, this is already available as a premise. Now, I have 3 and 4, A and B implies L. We can apply modus ponens to it, therefore, we get L, we get this L. Now, B and L implies M, it is there as a premise, and B and L 2 is there and L from 5 is there. So, using 2 and 5, if I combine C I using conjunction introduction, then I will get B and L. Now, B and L, it is already available as a premise here, B and L implies M is available. Now, we can use 6 and 7 and apply modus ponens to it, get M. Therefore, I can prove that through natural deduction rules, the knowledge base entails M. So, earlier we did that using some formula. Let us take this example. Can we try that? The first one, it is raining or it is sunny. It is raining implies I stay dry. It is raining implies I take umbrella. I take umbrella, then I stay dry. It is not sunny. So, how do we do that? It is raining is one proposition formula. P, we can call it as P. It is sunny, it is Q. So, it is going to be P or Q. It is raining, we can take it as P. Sunny, it is, we can take it as Q. Dry, we can take it as R. So, it would be P, first one would be P or Q. Second one, if it is sunny, then it is dry, or we can also directly as a statement itself, that is also fine. And if it is raining, I take umbrella, and if I take umbrella, I stay dry. So, we can map it to this fashion, P implies R and S implies T and T implies R, and we also say it is not sunny. Can we prove that given this, can we prove that I stay dry? Can we prove R? How do we prove R? We can use the natural deduction rules again and again to say that we can reach R. And how do we do that? It is not sunny and it is sunny is there. A implies B, P and Q not Q, therefore, we get P. See here, if you take P, first one is not Q and P or Q, you apply disjunction elimination, we get P, and now we get P with P and the result of this P with P implies R, which is in 2, we get R. Therefore, we can say that this knowledge base, this is for the knowledge base here, this entails R, or I stay dry is proved. Is proven. Now, this is a very simple way of doing according to our understanding, but systematically how do we write that is by means of this, having one as a premise, second line as a premise, and which rule we will use with the line numbers and the comments, we have to write it in a neat fashion, so that there is a proper proof for it. Okay. So, this is just a simple method for our understanding that we are doing. Again, take this example, a toddler implies child, and if a child, if it is a child and it is a male, then it is a boy. An infant is a child and a female is a girl, is a female. Can we prove that knowledge base implies entails girl? You can use the same formula and same type of the deduction rules that we have and prove that knowledge base entails girl. You finish off also this question in the next class. We will discuss the answer for this. And a summary of this session. In this session, in the last session and this session, I am just concluding. What we have seen is the syntax and the semantics of logic, and we did the truth table first, followed by some terminologies like satisfiability, tautology, contradiction, followed by the natural reduction rules. Most probably we will be using 4 or 5 natural reduction rules, which consist of the conjunction introduction, conjunction elimination, disjunction elimination, and the rule that we will be using mostly is the modus ponens. And with that, we also did 1 or 2 sample problems on the forward checking of the proof. So, with that I am concluding this session. In the next session, we will be starting off with the predicate logic.